Good morning. My name is Anaparthi Sammakka, final year MSc Ed Physics from Regional Institute of Education NCRT Mysore. Today in this video we are going to discussing about the properties of nanoparticle in comparison with bulk. So, when materials are reduced from bulk size to the nanoscale, their physical and chemical properties change significantly. And nanoparticles often exhibit unique optical, electronic, and mechanical behaviors that do not occur in bulk size materials. Let us talk about nanoparticles. What are nanoparticles? Nanoparticles are extremely small size particles, typically having sizes between 1 and 100 nanometers, at least in one dimension. Because of this very small size, materials at the nanoscale behave differently from their bulk form, and they can show unique physical, chemical, and optical, electrical, even magnetic properties. You can see here some common examples of nanoparticles include gold nanoparticles, silver nanoparticles, and quantum dots. The image here shown is a scanning electron microscope image of silver nanoparticles, or you can say SEM picture of silver nanoparticles. Here in this picture we can observe silver nanoparticles distributed across the surface. They appear as small bright grains. The bright grains see here are individual nanoparticles, each much smaller than 1 micrometer. Coming to the bulk materials are substances in their ordinary large sized form where the particle size is much greater than 100 nanometers, typically ranging from micrometers to centimeters. In bulk materials, atoms behave collectively and quantum effects are not noticeable. Because of this, their physical and chemical, optical, magnetic properties follow classical laws and remain stable. These materials have a relatively low surface to volume ratio and low reactivity compared to nanoparticles. You can see common examples including gold bars, silver spoons or wires, nails, etc. The image shown here is a piece of bulk gold representing how materials look in their normal macroscopic form. Like it is large, continuous and without the unusual size dependent effects seen at the nanoscale. Let's compare two forms of the same material. Bulk material means the normal everyday form that we can see and touch like a gold bar or an iron rod. In this form, the particles are very large compared to the nanoscale. So the material behaves in a usual way and its properties do not depend much on size. Coming to the nanoparticles, they are extremely small, say thousands of times smaller than the thickness of a human hair. When materials become this small, their behavior changes and surface atoms play a big role and quantum effects start appearing which can change color, reactivity and other properties. Now look at these pictures. The small colored bottles show gold nanoparticles. Even though it is gold, the colors are different because the particle sizes are different. Below that is bulk gold, which keeps it normal yellow color. Surface to volume ratio is the important reason that nanoparticles behave so differently from bulk materials. When a material is reduced from bulk size to nanoparticles, a much larger fraction of its atoms moves to the surface rather than staying inside. In bulk materials, most atoms are in the interior, so only a small number are available to interact with the surroundings, or say only surfaces of that bulk material can interact with the surroundings. But in nanoparticles, many atoms are exposed on the surface, which makes the material behave very differently. Because surface atoms have fewer neighboring atoms, they are more chemically active and unstable compared to atoms inside the bulk. This is why nanoparticles often show higher chemical reactivity and making them excellent catalysts. And the example of gold, bulk gold is chemically stable, but gold nanoparticle can act as very effective catalyst because so many atoms are available at the surface. The increased surface to volume ratio also affects other properties, like the melting point usually decreases because surface atoms are less tightly bound and need less energy to escape. And mechanical strength and electrical conductivity can also change due to the large number of surface atoms and grain boundaries. On the right side, the picture visually compares a single large cube and with many small cubes. Even though the total amount of material is similar, the nanoparticles expose much more surface area. Quantum confinement is the other big reason that nanoparticles behave so differently from bulk materials. Let's see what is quantum confinement effect. Quantum confinement occurs when the size of a material becomes comparable to the wavelength of its electrons. In bulk materials, electrons move freely and energy levels form almost continuous bands. In nanoparticles, electrons are restricted to a very small region of space. Because of this restriction, only certain discrete energy levels are allowed. The spacing between these energy levels increases as the particle size decreases. So this leads to changes in the band gap of the material. Smaller nanoparticles usually have larger band gaps, while larger ones have smaller band gaps. Due to this effect, optical properties such as color and light absorption change with the particle size. So, quantum confinement is responsible for the size-dependent behavior seen in quantum dots and other nanostructures. You can see the image. It compares the energy band structure of bulk materials with that of quantum dots and shows how the electronic energy levels change as the particle size decreases. See, left side of this picture shows that the vertical arrows represent energy increasing upward. In a bulk materials, electrons occupy two main bands. They are valence band and conduction band. So, in bulk solids, these bands are continuous, meaning electrons can have many closely spaced energies. So, the band gap has a fixed value for that material. And coming to the right side of this picture, there are quantum dots, and instead of continuous bands, you see many discrete horizontal lines. And these lines represent allowed energy levels caused by quantum confinement. So the colored circle at the bottom represent different particle sizes. So smaller quantum dots require more energy to excite an electron, and they absorb or emit higher energy light, and larger dots emit lower energy light. So this size dependent band gap is why quantum dots can glow in different colors. Coming to the chemical reactivity of nanoparticles compared with bulk materials. Here, nanoparticles are far more chemically reactive than bulk materials because a very large fraction of their atoms are located at the surface rather than inside the material. This extremely high surface to volume ratio creates many active sites where chemical reactions can take place. As a result, nanoparticles are widely used in catalysis and in sensors, fuel cells, pollution control, and in medical treatments also. A famous example is gold. In bulk form, gold is chemically inert and rarely participates in reactions. However, when gold is made into nanoparticles, its behavior changes significantly. At the nanoscale, gold develops highly reactive surface sites that allow molecules like carbon monoxide and oxygen to absorb, interact, and react to form carbon dioxide. This is something ordinary bulk gold cannot easily do. This striking difference clearly shows how reducing size to the nanoscale can completely transform the chemical properties of a material. Let us now compare the optical properties of bulk materials and nanomaterials. In bulk materials, optical behavior is mainly determined by the material's composition, and their color and transparency remains essentially fixed, and changing the size does not significantly alter their appearance. For example, bulk gold always looks yellow while bulk silver appears shiny white. However, when these same material are reduced to the nanoscale, they begin to exhibit unusual optical properties. The color of nanoparticles can change dramatically with particle size. This happens because of quantum confinement effects and a phenomenon called surface plasmon resonance, where electrons at the surface collectively oscillate in response to incoming light. As a result, gold nanoparticles can appear red or purple and silver nanoparticles can look yellowish. This striking difference shows that at the nanoscale, size itself becomes a powerful tool for tuning how materials interact with light. Let's see how the mechanical properties change when materials are made very small and down to the nanoscale. Nanostructured materials become much stronger and harder because they contain many grain boundaries. And these boundaries stop defects from moving easily, so the materials does not deform quickly. Because of this, nanomaterials resist surface damage better and can handle repeated stress for a longer time. Bulk materials, on the other hand, have larger grains that makes it easier for defects to move, so they bend and stretch more easily. But they are not as strong and the surfaces get damaged more easily compared to nanomaterials. That's why nanomaterials are used in things like airplane parts and lightweight car components, sports gears, and protective coatings. When we compare thermal properties, bulk materials behave in a stable and in a predictable way. They melt at fixed temperatures, conduct heat normally, and expand gradually when heated. But when the same material is reduced to the nanoscale, its thermal behavior changes dramatically. Because nanoparticles have an extremely large surface to volume ratio, many atoms lie on the surface and are more weakly bonded, which causes the melting point to drop significantly compared to bulk solids. Heat flow also changes since vibrations carrying thermal energy are scattered at the many boundaries between particles, often reducing thermal conductivity. Nanoparticles can expand more with temperature and store heat differently. Because of their small mass, heat up and cool down much faster than bulk materials. These unusual thermal responses make nanoparticles useful in applications such as thermal sensors, heat management coatings, and nano heaters and high performance insulating layers. Let us first look at magnetic nanoparticles. At this extremely small size, the nanoparticles usually behave as super paramagnetic. This means each particle contains only a single magnetic domain rather than many domains like in large materials. Because of this, when an external magnetic field is removed, the particles do not retain magnetization. This property is actually very useful, especially in biomedical applications such as targeted drug delivery, MRI contrast agents, and cancer therapy. Because of the particles can be controlled using a magnetic field and then safely dispersed once the field is turned off. On the other hand, bulk magnetic materials behave quite differently. They consist of multiple magnetic domains, and when exposed to a magnetic field, these domains align and the material can retain magnetization even after the field is removed. That is why bulk materials often act as permanent magnets, which are commonly used in motors, generators, and everyday magnetic devices. This table summarizes the key differences between nanoparticles and bulk materials. Chemically, nanoparticles are far more reactive and act as excellent catalysts, where bulk materials generally show low reactivity. Optically, nanoparticle display size-dependent colors due to quantum and plasma effects, while bulk materials maintain a fixed appearance. So coming to the thermal properties, in terms of thermal behavior, nanoparticles melt at low temperatures and show altered heat flow, whereas bulk materials have stable melting points. So magnetically, nanoparticles often become super paramagnetic and behave as a single domains, while bulk materials can retain permanent magnetism. So mechanically, nanostructured materials are usually stronger, harder, and more wear resistant, whereas bulk materials are softer and more ductile. In this slide, we can see the some advantages of nanoparticles compared to bulk materials. First, surface area. Nanoparticles have a very large surface to volume ratio compared to bulk materials. Because of this, they show much higher chemical reactivity. And due to this large surface area, their chemical reactivity is very high, which is useful in applications like sensors, medicines, catalysts, where bulk materials usually show lower reactivity. When we look at optical properties, nanoparticles can display special colors and absorption effects because of their extremely small size. Bulk materials, on the other hand, usually show fixed optical behavior. In terms of electrical properties, the conductivity of nanoparticles can be tuned or modified, while in bulk materials it is mostly constant. For thermal properties, nanoparticles may have different melting points and heat conduction compared to bulk materials, but where bulk materials generally follow normal thermal behavior. And regarding mechanical strength, nanoparticles are often stronger and harder when used in composites, while bulk materials are usually weaker for the same mass. Finally, for material efficiency, even a small amount of nanoparticles can give high performance, but bulk materials often require more material to achieve similar results. Now let us look at some limitations of nanoparticles when compared with bulk materials. First is large scale production. Nanoparticles are difficult to manufacture uniformly on a large scale, while bulk materials are much easier to scale up. Next is production cost. Nanoparticle synthesis is often expensive and technologically demanding, whereas bulk materials are usually cheaper to produce. Another important issue is environmental effects. The long-term impact of nanoparticles on health and the environment is not fully known, while bulk materials are generally easier to control. In terms of stability, nanoparticles tend to agglomerate, meaning they clump together, which can change their properties. Bulk materials are normally more stable. For reproducibility, the properties of nanoparticles can change with size and shape, making results harder to repeat, while bulk materials show consistent properties. Finally, regarding handling and storage, nanoparticles often require special conditions, whereas bulk materials are easy to handle and store. In conclusion, nanoparticles are not just smaller version of bulk materials, they are materials with entirely new capabilities. Their large surface area and quantum effects make them ideal for life-saving medical treatments, advanced electronic devices, efficient energy system, and powerful environmental technologies. From targeted drug delivery and quantum dot displays to clean energy and pollution control, nanoparticles are reshaping modern science and industry, and understanding how and why their properties differ from bulk materials allows scientists to design smarter, safer, and more sustainable technologies for the future. Thank you for watching.